Although in the previous lectures, we have developed a synchronous machine model using the basic parameters like the inductances, mutual inductances, resistances, etc. In the previous lecture, we had introduced the concept of system identification or obtaining the parameters of the model from measurement, and we discussed one simple frequency response test which could actually give us some parameters of the model. Unfortunately, when we do a test like a frequency response test, what we actually get are the coefficients of a transfer function, okay, that is obtained by fitting the frequency response obtained by measurement onto a transfer function of a certain order. Okay. So, that was what we get from measurement, and after we get that from measurement, we need to back calculate the basic parameters from it. Okay. But the major issue there is that if you don't have an adequate number of measurements, you may not be able to get all parameters required for the model. Okay. So, that was the basic point which I tried to emphasize in the previous lecture. Now, in today's class, we will try to get a synchronous machine model based on parameters obtained by measurement, and the title of today's lecture therefore is Synchronous Machine Models Using Standard Parameters. We will quickly recap our synchronous machine model. If you recall, the basic parameters of a synchronous machine were obtained as follows. So, you have essentially the flux current relationships, psi d, psi f, psi h are the d axis coils, the flux in the d axis coils, and they are related to the d axis currents. These of course, this model of course is in the basic parameters, okay, and it is obtained with k d is equal to root 2 by 3. And there are of course two differential equations associated with the field winding and the H damper winding. We also have a differential equation which is missed out being written here, that is corresponding to the d axis flux psi d. Now, if you take the Laplace transform of this is what we did last time, you get these equations, and from these if you get rid of psi f of s, psi h of s and I f of s and I h of s, we get a input output or transfer function relationship between psi d, I d and V f of s. Recall that V f of s is the field voltage, the voltage applied to the field winding. So, this is the nature of the transfer functions you get from this model. Okay. Of course, in addition to these differential equations, let me again emphasize, there is an additional differential equation corresponding to d psi d by dt, which you have not written here, but we shall write it down shortly. But if I want to get a transfer function relationship between psi d and I d by eliminating psi f of s, psi h of s, I f of s and I h of s, I essentially use the algebraic equations, the first three equations which are algebraic equations. The latter two equations are also algebraic equations, but they are obtained effectively from differential equations on which we apply the Laplace transform. Okay. So, all of them in fact are algebraic equations. So, what we see that it eventually leads us to a second order transfer function L d of s and g dash of s, and the nature of the transfer function looks like this. Of course, the coefficients a n, b n, a d and b d and a g are in fact related to the basic parameters. So, if you just solve these algebraic equations and get a transfer function relationship of this form, you shall find that b n, a n, b d, a d, a g are related to the basic parameters by these equations. Okay. So, for example, a g is dependent on a LHH, RH, MDH, LFH, MDF and RH. Okay. So, these are essentially what we get from the original model. Okay. So, from the original model we can get a transfer function, the transfer function is in terms of basic parameters. Now, if you carry out a measurement with V f is equal to 0, this is something we discussed in the previous lecture. if we carry out a measurement, what we will effectively get are again the coefficients of the transfer function, or equivalently we will get these time constants T d dash, T d double dash, T d 0 dash, T d 0 double dash and L d. Okay. Now, of course, AN, BN, BD and AD are related to these time constants by the 4 equations given there. Okay. So, what we have here is some parameters obtained from measurement, okay, the AN, BN, BD, AD parameters obtained from measurements, and the basic idea is that why don't we back calculate the basic parameters from these. Okay. Now, if we could calculate the basic parameters from these, we could actually use our model in realistic studies. So, that is what the basic idea is. Okay. But you will notice that there is already a low roadblock. If you just use this one measurement, then we have a problem. Okay. Why is there a problem? Because the number of basic parameters are more than the parameters obtained from measurements. Okay. So, what we obtain from measurement are simply L d, T d dash, T d double dash, T d 0 double dash and T d 0 double dash, okay, which are the effectively give you the coefficients of the transfer function, from which we have to back calculate the basic parameters. Now, of course, you could do another measurement. For example, you could obtain the transfer function g dash of s, okay. That is, you obtain a transfer function of psi d with respect, rather psi d given V f as an input, and obtain this transfer function given here with I d is equal to 0. So, effectively, if you look at this transfer function, if I set I d is equal to 0 and give V f as an input and they take out the transfer function g dash of s, we will essentially obtain M d f by R f and T d c double dash. So, M d f by R f as a whole we will obtain, okay, and the time constant T d c double dash. So, this is what the transfer function will yield, or this measurement will yield. Of course, it presumes that you know T d 0 dash and T d 0 double dash from the previous measurement also. So, this is what we get. Of course, this T d 0 dash and T d 0 double dash also can be obtained from this measurement itself by curve fitting the frequency response. Okay. So, this is what we can get if we carry out 2 measurements, but unfortunately, in most of the synchronous machine literature, they do give us the parameters obtained from one measurement. Okay. So, we typically do not have this the value of T d c double dash and M d f by R f. Okay. In most studies, actually it is not very difficult to get this, but often the data set which is provided to you will not have the information relating to this M d f by R f as a whole and T d c double dash. This is typically not available, okay, but in principle it could be. Okay. So, what I will describe to you is what typically will be available to you and what you can do with it. Okay. So, for example, you have got only one measurement and you are given these standard parameters L d, T d dash, T d double dash, T d 0 dash and T d 0 double dash, and the model parameters which you need to get are L d, M d f, M d h, L f f, L f h, L h h, R f and R h. So, this is what you need to get from the standard parameters, but unfortunately, you can't get all of them because the number of parameters exceeds the standard parameters. Okay. So, we can't back calculate it. What we have effectively is from this, if you look at this, we can get 5 equations from here. We can get L d, and we have got these 4 algebraic equations which we can equate to A n, B n, B d and A d, which are in fact these. But obviously, if the number of equations is less than the number of parameters, then you can't back calculate all the basic parameters. Okay. The standard parameters are lesser than the number of basic parameters. So, we can't really get all of them. Okay. Of course, the solution to this is have more measurements, okay, but I am describing to you a situation where you have only these parameters given to you. Okay. So, one can't get a unique solution for the model parameters with just one transfer function measurement, but this is what is typically available to you. Of course, we also require stator resistance. This is something I did not emphasize. We also require stator resistance. It is usually a very small value, but it can be obtained separately. So, whenever I talk of standard parameters, implicitly I also mean the stator resistance, okay, which can be obtained easily from measurement. Okay. So, we have got 5 measurements, 5 standard parameters here given here, and we have to get the basic all the basic parameters. It is not possible to do that. Okay. So, we are actually having a kind of a situation where we cannot get all the parameters required for the synchronous machine model which we have derived. Okay. So, let us see how we can work around this. Okay. Now, if you look at a similar situation exists in the q axis winding. Okay. So, this is the basic equations of the q axis excluding the differential equation corresponding to d psi q by dt. Okay. The differential equation which tells us how d psi q by dt is related to the other variables is missing from here, but we shall include it later. Okay. Now, if you look at this, also a similar situation exists. If you take out the transfer functions as before, this is what we get. Of course, there is all the damper windings are of course shorted. You do not have any voltage applied to the damper winding. So, you do not really have that additional transfer function g dash of s as in the d axis. So, of course, the coefficients of this transfer function are related to the basic parameters by these equations. Again, we follow the same procedure to obtain the basic parameters, but we end up with the same problem that you have got 8 basic parameters on the q axis, and typically the standard parameters are only 5. Okay. So, getting back the basic parameters becomes a bit tricky. Now, so what is the way around this? There are 3 possibilities. Okay. Now, one of the possibilities is use a state space model which requires fewer parameters. You can do that. I mean, we require 8 parameters to get the original model in the original states, that is the stator and rotor fluxes. Okay. But one can imagine that one can take out a state space model which requires fewer parameters and is in terms of other states, okay, states which are algebraically related to the stator and rotor fluxes. We discussed this in the previous lecture, where there is no unique way to obtain a state space model from a transfer function. Okay. So, what we can do is, if you have got a transfer function, do not put a condition that you should write the equations in terms of the basic the original states, that is the stator and rotor fluxes, but we will write it in terms of states such that the state space model requires fewer parameters. Can you do it? Yes, you can do it. We shall show you shortly. So, the first possibility is use a state space model which requires fewer parameters, but the states cannot be easily related to the original states, okay, which are the stator and rotor fluxes. So, that is model A. The other possibility is use a state space which requires fewer parameters, but by making certain approximations and assumptions, we try to obtain the state space model in terms of states which can be related very easily to the original states. That is, so I write down my state space model, and the model which I get essentially is in terms of states which can be easily, for example, it is proportional to some. For example, we can have a state psi maybe psi f dash, as I will show you shortly, which is proportional to the original state, okay, which is the rotor flux psi f. Okay. So, we can try to write down the equations in terms of states which are related to the original states very easily. Okay. So, we of course, we will need to make some assumptions, as I will mention shortly. So, we do of course need to back calculate from the standard parameters the parameters required for this state space model. So, we will call this model 1. Okay. So, model A is a model without any approximations, but is a state space which requires fewer parameters, but the states cannot be easily related to the original states, which are the stator and rotor fluxes. The second possibility is we will use a state space which requires fewer parameters, but it is an approximate model which makes certain assumptions. But the good thing about this model 1 is that the states are very easily related to the original states. Okay. The third possibility exists is to use a state space which requires fewer parameters and has all the properties of model 1, but the good thing about this model 2, which I shall also talk about, is that you do not have to do this extra step of back calculating the basic parameters. You will write down the state space in terms of the standard parameters itself. Now, this all may sound a bit confusing to you. It is somewhat confusing, but as we go through the models, I am sure you will understand what I am trying to say. So, just let us look at model A. Suppose I have got the standard parameters. So, let us just go through model A. So, model A is a state space model which requires fewer parameters. In fact, it will directly use the standard parameters, but the states cannot be easily related to the original stator and rotor fluxes. So, remember that model A, model 1, model 2 will have the same transfer function, okay, but remember the main theme or main crux of what I was trying to say is that we try to take out a state space model which use the standard parameters in some way. Okay. So, let us focus our attention on first the q axis. Okay. The q axis transfer function is given by LQ into this second order transfer function. Okay. So, in fact, rather I should say that this is a second order transfer function and it has got 5 parameters here. Okay. 4 time constants and 1 overall you can call it a gain, okay, LQ. Okay. Now, one point, one small diversion which we shall have right now is that you can write the same transfer function in this form. How is this form different from this form? First of all, this is the transfer function of psi q with respect to IQ, psi qs upon IQs. Okay. IQs upon psi qs is simply the reciprocal of this transfer function. Okay. Now, what I do is I write this IQs upon psi qs, okay, in this fashion. I rewrite it in this fashion, but you will notice that instead of using TD 0 double dash and TD 0 dash, I am using now new parameters LQ dash and LQ double dash. Okay. So, this transfer function is the reciprocal of the earlier transfer function, is written in terms of LQ dash, LQ double dash, okay, and the time constants TQ dash, TQ double dash and LQ. Now, before you start getting a bit confused about what I am getting at, what I really want to say is that instead of giving you LQ, TQ dash, TQ double dash, TQ 0 dash and TQ 0 double dash, I can just as well give you LQ, LQ dash, LQ double dash, TQ 0 dash and TQ 0 double dash. Now, what I mean to say is that I can give you either the first set of parameters or the second set of parameters or the third set of parameters, but they are all interrelated. Okay. So, they are basically 5 standard these 4 time constants and LQ. Okay. But you can also give instead 3 inductances, that is LQ, LQ dash and LQ double dash and 2 time constants, okay, with the understanding of course that all these parameters are related to each other. Okay. So, the same transfer function can be written like this, where the time constants and the reactances are related to each other in this fashion. Okay. So, you may find sometimes the data which you get, you may find the first 5 set of parameters given to you, or you may find the next set of parameters given to you, or you may find LQ, TQ dash, TQ double dash, LQ dash and LQ double dash given to you. Okay. And of course, the stator resistance also will be given. Now, all these sets of data are equivalent in some way, because there is a relationship between LQ double dash, LQ dash and the time constants. Okay. So, if you look at this relationship again, it is this. This can be easily checked by equating. You can actually write this in numerator polynomial by denominator polynomial form and take the reciprocal of this and equate it to this. Okay. If you do that, you will get this interrelationship. Okay. Now, why did I have to get this suddenly into the picture? Because the model A, which I am going to describe to you, can be conveniently written down in terms of reactances and the time constants TQ dash, TQ double dash. Incidentally, I have not described to you what these inductances and time constants are called. LQ dash and LQ double dash in these equations, okay, are in fact called the transient and subtransient inductances of the synchronous machine. Okay. And TQ dash and TQ double dash are called the short circuit time constants of the synchronous machine. Okay. The short circuit transient time constant is TQ dash, the short circuit subtransient time constant is TQ double dash. Okay. Similarly, TD0 double dash, TD0, TQ0 dash is the transient open circuit time constant and TQO double dash is the subtransient open circuit time constant. Okay. So, we have got TQ dash and TQ double dash, which are the short circuit time constants, LQ dash and LQ double dash, which are the transient and subtransient reactance inductances, and TQ0 dash and TQ0 double dash, which are the open circuit transient and subtransient time constants. Okay. This is what they are called. Why are they called so? This will become clear in a couple of lectures from now when we do the short circuit and open circuit analysis of a synchronous machine. The model A, let us again get back to what we were getting at. We are trying to get a model based on the standard parameters, okay, which uses just the standard parameters. Okay. But I just introduced one small issue or point here, that instead of giving you 4 time constants and the reactance and the inductance LQ, sometimes you are given 3 reactances and 2 time constants, but the point is that they are all interrelated. Okay. So, if you get this data, do not get suddenly perturbed. Okay. You can get the time constants from the reactances, okay, by this interrelationship. Okay. So, you are normally given these any of these 3 sets of parameters. Okay. They can be they are all, the parameters are interrelated by this. Okay. So, what I will do is now give you a q axis model. Okay. It is a state space model which is using only the standard parameters. Okay. Instead of course, TQ0 dash and TQ0 double dash, I am using the inductances LQ dash and LQ double dash, but remember that they can be obtained from one another. Okay. So, really we are in fact using the 5 standard parameters itself. Okay. Now, one of the points which you should remember here, that psi, what I have done is psi q is of course the state we know, psi g and psi k I have used the uppercase subscripts to denote that these are not the original psi lowercase g and psi lowercase k. Okay. These are states, psi uppercase g and psi uppercase k are states which are linearly related to psi g and psi k. Okay. But that in fact that interrelationship is something which we do not know. All we know is that this is one model which will also give you, the same transfer function as before. Okay. So, this is something you should this is what I want you really to get, that this particular transfer function which you are getting here, this particular state space model which you are getting here is in fact using only the standard parameters, okay, but psi uppercase g and psi uppercase k are, we know they are related to psi lowercase g and psi lowercase k, which are the original rotor fluxes, but we actually do not know what that interrelationship is. All we know that this is a state space model which will yield the same transfer function as before. Okay. Actually, this is not a really a big problem. In fact, psi g and psi k, okay, psi uppercase g and psi uppercase k are states which are related to psi lowercase g and psi lowercase k, but unless we are really interested in knowing the fluxes through the damper winding, okay, or the currents through the damper winding for that matter, okay, it is okay to use this model. Okay. So, psi q is of course as before, okay, which is the flux through the q axis winding, but psi uppercase g and psi uppercase k, it is difficult to assign of, they are related to psi g and psi k, are lowercase g and lowercase k. But unless we are really interested in knowing what the damper winding fluxes are, okay, it is all right to use this model, because as far as the stator is concerned, as far as the transfer function we obtain from this model is exactly the same as can be obtained from the original state space model. Okay. So, this is an acceptable state space model which yields the same transfer function, okay, as this transfer function. Let us just show, I will just show it to you. So, you can actually work this out. It is a bit of an exercise, but you can show that this particular transfer function, this particular state space model will give you the same transfer function relationship between psi q and I q as given here. Okay. So, this is something which you should, you can actually work it out. All you have to do is, for example, take the Laplace transform of psi g, the first differential equation and the second differential equation and the third algebraic equation, and you should be able to get this interrelationship. In this particular state space model, I have also written down the differential equation for psi q, d psi q by dt. So, just to make things a bit clearer, I will just indicate the steps you need to go through to verify that model A indeed gives you the transfer function which I had just shown you some time back. So, for example, what you need to do is, you take the transfer function of the first differential equation, s into d psi g of s is equal to 1 upon, so this you can write as t q dash is equal to minus psi g of s plus psi q of s, and this is t q double dash s psi k of s. This is uppercase k, just to differentiate this from the original state. Okay. So, this is what we get. So, in fact, you can, from this you get psi g of s is equal to psi q of s upon 1 plus s t q dash, and psi k of s is equal to psi q of s 1 plus s t q double dash. Okay. So, and we also have psi q of s is equal to L q I q of s, we will write this like this, I q of s plus L q dash minus L q double dash upon L q dash psi k of s plus L q minus L q dash upon L q psi g of s. Okay. So, you can look at the slide. What I have essentially done is obtained the Laplace transform of these equations, the first three equations, and if you look at if you follow the steps, now it is quite straightforward. What we need to do is, of course, psi g of s, psi q of s is now equal to L q double dash I q of s plus L q dash minus L q double dash upon L q dash into psi q of s. Now, psi k of s, psi uppercase k of s is nothing but psi q of s upon 1 plus s t q double dash, okay, plus L q minus L q dash upon L q double dash on L q dash into psi q of s upon 1 plus s t q dash. So, what what we are really doing here now is it must be quite apparent to you. We are trying to get the transfer function relationship between psi qs and iqs. Of course, the next step would be take this onto this side and this whole term also onto this side, okay, and thereby get a relationship between iq of s and psi q of s. And what you need to verify is that this yields this particular equation eventually will lead you to this, okay, which is equivalent to this. Okay. So, this is what I need you to just work out. Okay. So, our q axis model A, we can actually use this model, the q axis model. Okay. Note that it also includes the differential equation of psi q, d psi q by dt is equal to omega psi d minus R A into I q minus V q. Okay. This model can be used directly now, okay, for the q axis. Okay. If you have got the standard parameters given to you, you just use this model. Okay. If somebody asks you what is, for example, tell me the flux, okay, the flux in Tesla of the G damper winding, the answer is I can't find it out. Why? Because the state psi g and psi k, the uppercase states are valid states of course, but they are related to psi lowercase g and psi lowercase k, which is the original rotor fluxes. Okay. But that relationship is not known. This is something I am not giving you. All I am assuring you is that by using this particular state space model, you can get the same transfer function as before. This is a valid state space model of which yields the same transfer function. So, you can use it. Okay. You can use it provided you do not require to know what actually the actual G and K damper winding fluxes or currents are. Okay. Just remember that. But nonetheless, in most studies we do not require to know exactly these fluxes. Okay. You only need to know what effect these fluxes have on the stator side. Okay. In that sense, this is a valid model because it gives you the correct transfer function relationship between the observables on the stator side, that is psi q and iq. Okay. So, that is the important point. In the d axis, if you remember that the transfer function relationships are as shown here. Remember that there is an additional transfer function here because you have got an input. The input is of course the field voltage. Okay. Again, instead of specifying 4 time constants or writing down the transfer function in terms of 4 time constants, I can write them in terms of 3 inductances and 2 time constants. Okay. That is okay, because the time constants and these inductances are in fact related by the relationship which is shown here. Okay. So, this is something you can work out, it is not very difficult to do that. What you need to do is of course equate this transfer function to the reciprocal of this, the first transfer function given in this equation. Okay. So, it is not very difficult to verify that this relationship holds. Okay. So, if you are given LD, TD dash, TD double dash, TD 0 dash and TD 0 double dash, you can in fact get the the inductances LD dash and LD double dash. Okay. So, your standard parameters could be in any form, either the first set, the second set or the third set shown in this slide. Okay. But with this you have got essentially whatever you require, you do not have to because of the interrelationships which exist. Okay. So, you will be given either of these set of either this, the first set or the second set or the third set. Okay. But using this any of these sets you could get the model you desire, because there is an interrelationship between reactances and the time constants. Okay. Stator reactances can also be obtained from measurement. So, I have not explicitly of course mentioned this, but yes, you can obtain stator resistance also from measurement. Now, if you look at the d axis model, remember that the state space model will have an input, rather I should say the rotor differential equations corresponding to the rotor fluxes, rather I should say the differential equations corresponding to the rotor fluxes will have an input term. Okay. This is not unlike the q axis. In the q axis, the damper windings have no voltage input. Okay. The Q winding, okay, of course, does have an input V q, okay, but there is no equivalent of a field voltage in the Q axis damper windings. Okay. So, damper windings are simply shorted, okay, but in the D axis one of the damper windings is shorted, the field winding has an input V f, okay, and of course, V d is an input to also to an input to the D winding. Okay. So, if you look at the inputs, you have got V f and V d. Now, what you notice is this is a state space model. This I am directly writing it down, I am just stating it without proof, that this is a valid state space model which yields the transfer function relationship this. Okay. So, all you need to do here, of course, to verify this is take the Laplace transform of the first 3 equations and get the interrelationship between psi d and I d, psi d of s and I d of s. You can verify that you will get exactly the same transfer function as given here. So, this is the nature of the model on the D axis, but remember there is one catch here. Model A, the state psi uppercase h and the state psi f uppercase f, okay, are not equal to psi lowercase h and psi lowercase f. Okay. Remember that psi lowercase h and psi lowercase f are in fact the fluxes through the H and F winding respectively. Okay. But if you look at the differential equations written here, they are not, they are using the uppercase subscripts just to indicate that these states are not the same as the original states. In fact, the relationship exists, a linear relationship, you can transform from these states to psi h and psi f lowercase, but that interrelationship is not known. And if you notice, this state has some some contribution of the input also included. So, obviously, this cannot be the original damper winding flux and this cannot be the original field winding flux, because now V f is kind of distributed amongst these two. In some sense there is the input directly affects psi uppercase h and psi uppercase f. Okay. So, these states are not the original states, but remember what I am trying to get at, this is a valid state space representation which yields the same transfer function. Okay. Insofar as the stator effects, that is the relationship between psi d and I d and the effects on the stator winding are concerned, you will get the same answer. But if somebody asks you the question, what is the field winding flux or what is the field winding current or what is the H axis damper winding flux, you will not be able to answer this question if you use this model, because these states are not directly or easily related to the original states, or rather I should say the relationship is not known. All I can say is that this yields the same transfer function as yields the correct transfer function or yields the correct interrelationship between the stator flux and the stator current, psi d and I d. Okay. But just remember this point. Okay. This is a valid state space model. Okay. Now, beta 1 and beta 2 of course, are rather complicated expressions. This is something you can verify at leisure. So, this is something I state without proof. This is a directly a d axis model. Okay. So, in fact, if you do not want, to know, okay, if you do not want to know what the stator, what is the rotor flux, rotor H winding flux or the field winding flux, you can still use this model for understanding the effects on the stator. Okay. So, this is one thing which you should keep in mind. So, this is a valid model, model A. Now, we go to model 1. Now, just because it is possible that it is kind of gets a bit tedious. So, let us just go back a few slides and remember what we are trying to do. We have got these parameters just from one measurement. If we had more measurements, we could have back calculated all the basic parameters required for the original model, which is in terms of rotor and stator fluxes. But what we are doing, what I shown you just now is model A, which requires fewer parameters, but the states in model A cannot be directly related to the original stator and rotor fluxes. In fact, the stator fluxes, I must make a small correction here. The stator flux psi q and psi d are retained in the model, but the rotor fluxes in fact are something are not retained in model A. Okay. So, model A is a you can use this model, the d and the q axis model, okay, but you will not be able to answer the question of any question about what the flux in the field winding and the H winding individually are. Okay. Model 1 is a model with approximation. So, now let us try to understand what we are going to do. We cannot get a model in the original parameters, okay, original basic parameters, because we often do not, we are not given adequate number of parameters from measurement. Okay. So, what we are going to do now is use model, introduce to you a model called model 1, which will use some assumptions and approximations, and what we will do is we will create a model using the original states or a small like states which are proportional to the original states. Okay. And what we will do is back calculate the parameters of this model from the standard parameters. Okay. So, this may again appear a bit confusing, it is a bit confusing, but I am sure after we go through the model you will understand what I am getting at. Okay. So, let us talk about model 1. Now, remember that the original equations on the d axis, this is the original model in terms of the basic parameters. Okay. Now, what I will do is I will try to obtain the same state space model in terms of new variables. Okay. So, the new variables are psi a, psi f, psi h dash, okay, so or prime. Okay. So, we are going to use psi f prime, psi h prime, I f prime and I h prime, which are related to the original states. But remember that this interrelationship which I am going to talk about is very straightforward, it is simply a proportional relationship. Okay. In model A, which we just discussed, I told you that there exists a relationship between the uppercase or the new states and the lowercase states, but that interrelationship is not given, it is not clear what does this interrelation, it is a linear transformation from one state to the other. Okay. Here also we are in fact using a linear transformation, we are just, but the interesting thing is psi f dash is just dependent on psi f. Okay. So, there is a direct kind of direct relationship between the new state variables which I am going to use and the old state variables. So, this relationship is direct or easy to understand, it is simply a proportionality relationship. Okay. So, if you look at the new d axis variables, okay, these are in terms of the old variables, but the combination or the relationship is very straightforward. Okay. When I say straightforward, what I mean is psi f dash is just dependent on psi f. Okay. In model A, in fact, this is not true. Psi f, the psi uppercase f would have been dependent on psi lowercase f as well as psi lowercase h. Okay. But in this particular model, we have got a direct relationship, and so you can even look at this interrelationship as if it is like referring the variables of the flux to the stator side. Okay. So, you have got distinct windings here F and H, and what we are doing is we are not bothering about what psi f and psi h are, okay, but we will refer them, we are not bothered in the sense that we are seeing what its effects are as when they are referred to the stator winding, okay, stator side. Okay. So, what we are doing is doing a kind of turns ratio kind of transformation. Okay. So, it is similar to referring the variables to one side of the transformer. Okay. Now, so you have got psi f, psi h, I f and I h. Okay. So, these are in fact the interrelationships which we are going to use. Okay. So, what if I use this interrelationship? Now, what will happen is, since I have changed the variables, your equations in the new variables will look like this. So, all the variables kind of have this prime except psi d I d, which you are going to remain as it is. Okay. But all the other variables are in fact replaced by the corresponding prime variables. Okay. Now, of course, MD, we have not defined what MDF dash prime or MDH prime and so on are. Okay. So, let us just define them. Remember that psi f prime, I f prime, psi h prime and I h prime are defined by these variables. Okay? They are these relationships. So, of course, it is easy to find it is easy to find that the new coefficients of these algebraic equations are actually given by these relationships. It is not very difficult to see this. Okay? This must be appearing to you similar to referring variables or resistances and inductances to one side of a transformer. Okay? So, in fact, it is similar, this whole operation is in fact similar. Now what we will do is make some simplifications, let us call them approximations or assumptions, okay, to reduce the number of parameters. Now, if you look at this model which we have, actually we have not reduced any parameters. The differential equation or the state space model in fact looks just as complicated as before. Okay. Now, to reduce the number of parameters, what we will do is, we will choose this alpha h, choose it. Okay. So, this is a very important word. We choose alpha h so that MDH dash is equal to MDF dash. So, what we are going to do is choose alpha h. Now, so if I am choosing it so that this relationship is satisfied, it means that I am using it in fact alpha h is something I do not know, but I am choosing it so that this relationship is being satisfied. Okay. Now, this also means that since I am choosing it to reduce the number of parameters, its original meaning as a turns ratio is no longer valid. Okay. So, alpha h is no longer the exact turns ratio, okay, between the damper H damper winding and the stator winding. It has been chosen so that we are reducing the number of parameters. This is okay because this is okay if we do not want to eventually know what exactly the current in the damper winding is in amperes. Okay. If somebody asks you what is going to be the damper winding current in amperes, if you make the first approximation, if you have chosen alpha h such that MDH is equal to MDH dash is equal to MDF dash, we will not be able to tell eventually what actually the damper winding current in amperes is, because I have chosen alpha h to satisfy this criterion rather than using the actual turns ratio. Okay. So, I am imposing a condition, I am using alpha h, not the actual turns ratio, but a value which will yield this. Okay. Now, the second point here is very important. If alpha f is the actual turns ratio between the stator and the field winding, then MDF prime is LD minus LL. So, we will talk of another parameter, in fact, it is an addition to the standard parameters. This LL is a leakage reactance, leakage inductance. Okay. So, if alpha f is an actual turns ratio, if I use actually the turns ratio between the stator winding and the field winding, then we shall see that in fact LL is a leakage inductance. Okay. Now, the third thing which I am using here is assume MDF dash is equal to LFS dash. So, actually by assuming this, I am reducing the need for one parameter. Okay. So, in fact, this is an ad hoc assumption, okay, without any justification. We have not given any justification for this. In fact, there are leakages which have to be accounted for. So, the third assumption is an ad hoc assumption. Okay. It is not based on some very realistic or very correct kind of reasoning, but just an assumption made to reduce the number of parameters. So, obviously, now we are talking in terms of approximations. So, what we are going to get is an approximate model, it is not the exact model. Okay. Model A was an exact model, it was a valid state space model. This is also going to be a valid state space model, but what we have made an assumption here. So, it is an approximate state space model. Okay. Alpha h is chosen based on trying to equate two mutual inductances. So, it is not going to be actually the turns ratio. Okay. We have chosen alpha h so that this is satisfied. So, we tweak the value of alpha h so that MDH dash and MDF dash are equal. Alpha f is the actual turns ratio between the field winding and the stator winding. So, MDF dash prime is actually LD minus a leakage. Okay. So, this is fine. So, the first and second points which are mentioned in this slide here are in fact okay, in the sense there is nothing wrong in what we have done here. Okay. But the third thing is certainly an assumption, okay, which will make our model approximate. Okay. So, let us just recap what we are doing. Model 1 is a state space model using certain assumptions. So, that the state space is in terms of states that can be related to the original states easily. What do I mean by that? This is an easy relationship. Okay. Alpha h and alpha f are in fact can be looked upon as turns ratios. You have simply referred things to one side of a transformer. So, that is essentially, so what we have done is writing down the state space equations in terms of referred states. Okay. But since referred states are simply proportional to the original states, this is not really a very, this is a kind of a reasonable or useful approximation to make. Okay. Alpha f we will keep as the actual turns ratio. So, psi f dash is in fact going to give you the referred field winding flux, sorry, the turns alpha f is in fact the turns ratio, we will use it as the turns ratio. Alpha h is something we choose, so that we make two mutual inductances equal. So, alpha h need not be the original turns ratio between the damper winding and the stator winding. Okay. So, this is something which we should remember, alpha h is chosen by us. One interesting thing is that if I write down my transfer functions in terms of the new states, okay, the original transfer function does not get changed, the form is exactly the same. Of course, it is in the equations also look similar, they are only using primed quantities. Okay. Everything else looks the same, which is not surprising. But the important thing is, because of the assumptions we have made, in fact, not the assumption, there is one assumption we have made and one additional parameter which we have to obtain from measurement. We effectively get 6 parameters from measurement, that is LD, TD dash, TD double dash, TD 0 dash, TD 0 double dash and LL, and the only parameters we need to get are LD, LFF dash, LHH dash, RF dash and RH dash. Okay. So, we now actually can compute. Okay. This is what I wanted to say actually. The parameters for this model are these, okay, and the parameters from measurement are the ones given below. So, we can actually get the parameters required for this model. Of course, you may say where is MDF prime, it is missing from here. Okay. Where is MDH prime? But recall what we have done. MDF in fact is LD minus LL, MDH prime is equal to MDF prime and MDF prime is equal to LFH prime. So, what we have effectively got here now, we have reduced the number of parameters by the one assumption we have made, by the choice of alpha h, the choice of alpha h member and this extra leakage measurement which will be required. So, this is model 1. Now, alpha f is the turns ratio, but actually when we write down this model, we will not require alpha f at all, provided V f dash is used in all the calculation, the referred voltage. Okay. So, although I have introduced this concept of alpha f or rather this turns ratio alpha f, it is not required in any of the calculations, provided of course, in all my calculations and all my studies, I am going to use V f dash, which is referred voltage. Okay. So, I will never specify what the field voltage is, but I will always specify what V f dash, which is the referred voltage. Okay. A similar thing can be, so the summary of the model in the model 1 on the d axis is this. So, this is the model which you will use. Okay. LFF dash, LHH dash, LD, LL, okay, RF dash and RH dash are going to be calculated from the standard parameters using the interrelationships between which we have discussed some time back, this. Okay. So, using these you can back calculate all the parameters required by this model. Okay. So, actually this is an interesting and important, and in fact, most books and the literature follow this kind of model. Okay. So, this is an important model, the model on the d axis. Actually, this is something which we have mentioned some time back. the q axis can be similarly found. Okay. So, model 1 is the model on the d axis and the q axis. This uses parameters back calculated from the standard parameters, okay, but it does make some approximations. Okay. In fact, once if we use these model on the d axis and the q axis and we get our answers, one thing we know, psi g dash which we get and psi k dash, psi f dash and psi h dash are going to be proportional to the field winding fluxes and the damper winding fluxes. So, there is a kind of a direct and direct relationship between the states, the primed states and the original states. So, this is a more satisfying kind of model, because the new states are in fact related to the old states. Okay. Now, what about model A? Isn't model A valid? The model A is also valid, but in model A it is difficult or not possible, okay, to tell what the actual field flux or the damper winding flux is going to be, not even the referred value. In model 1, we at least know the referred value of these fluxes and currents, we can do that. Model A, though an exact model obtained from standard parameters, you cannot do this. Okay. So, this is the difference between model 1 and model A. Model A is correct, exact, uses standard parameters. Model 1 is an approximate model, but the fluxes here and rather I should say the states here and the currents here are easily related to the original states. Okay. Now, in the next class what we shall do is talk about another model, model 2, okay, which uses a distinct approximation, okay, but it has an advantage that this back calculation step will not be there. You know, if you look at model 1, there is a back calculation step involved, in the sense that you have got a standard parameters, but you still need to back calculate. If you look at this slide, you still need to back calculate LFF dash, LHH dash, RF dash and RH dash and LL. Okay. This is not a problem really, but we shall just look at another model, model 2, which is more convenient. Okay. So, this back calculation step we can avoid. Okay. So, let me just clarify again what we are trying to do and summarize today's lecture. We have got the standard parameters obtained from measurement. If we do not have adequate number of measurements, or we given a limited amount of measurement data, which is typically the case, we will be given limited amount of measurement data, we have to build our model. Okay. We can build in fact a model, a state space model which uses fewer parameters, but we are stuck with the problem that the rotor fluxes there and the rotor currents there in that model cannot be easily related to the original rotor fluxes and currents. Okay. On the other hand, if you use model 1, okay, we call this model 1, which is most popular model in some ways, we can we are using fluxes and currents which are related very simply, simply by a proportional relationship or a referred relationship with the original states. Okay. But of course, model 1 does involve an approximation. Okay. We shall in the next lecture introduce to you model 2, another model which uses a distinct assumption, but does not require this back calculation step which is required as shown in this slide here. You need to back calculate these parameters from the standard parameters using the relationships, these relationships. Remember that model 1 involves an assumption. Okay. The IF dash and psi f dash obtained from this model, IF prime and psi f prime rather, which you get from this model, are directly going to give you the referred value of the field winding flux and currents. Okay. IH dash and psi h dash or IH prime and psi h prime are in fact going to be proportional to the damper winding flux and current, but the exact proportionality relationship cannot be obtained from this model. In fact, if somebody asks you the question, if I use this model, can you tell me what the damper winding current in amperes is going to be? He will not be able to answer this question. If somebody asks you what is the field current going to be in amperes, you still can't answer this question, but if somebody actually tells you the turns ratio between the field winding and the stator winding, yes, you can answer that question. Okay. So, this is the important thing to be kept in mind. Okay. So, we can have a d axis and a q axis model 1, which is the most popular model which is used in the literature. In the next class, we shall do model 2, okay, and we shall also discuss equivalent circuits and the per unit model. So, using this, we will be all set to study a synchronous machine and do in fact realistic studies, because these are the parameters, standard parameters are the parameters which will be available from measurement. Is it okay? So, we will continue our discussion in the next lecture.